Hello everyone, welcome back to another video in segment tree series. If you are new, this is a new series that we have started in which we are trying to dissect segment trees from scratch. We already have 12 videos in this series in which we have started all the way from basics of segment tree, how to build segment trees, when to use segment trees, how to do point updates, range queries. We have discussed the complexity analysis of each of these methods along with their involved proof, and then we have solved questions of different difficulties on various categories. We started with problems involving queries on the prefix of an array. We then looked at how the segment tree structure looks very similar to how binary search proceeds. So whenever we can use segment tree itself to do binary search, so we looked at that concept and looked at some of the problems on that. We then looked at merge sort trees and then solved a couple of problems on that as well. In the last video, we have discussed about persistent segment trees. We already have a well-maintained Google Doc in which I have mentioned all the relevant videos and the practice problem related to that video. If you are new to segment trees or if you want to strengthen your understanding of segment tree, you can go through this list, and I'm very sure it will help you strengthen your understanding about segment trees. So in this particular video, we will be solving the KQuery problem. In particular, we will be focusing on the code of persistent segment trees, and in the next video we'll be looking at how persistent segment tree is different from merge sort tree and when to use what, right? So this video will be focused on mostly on implementation and solving KQuery. So let's just quickly look at the problem statement first. So the problem is straightforward. We have given a n number array and a number of k queries. A k query is a triple ijk for which we have to return the number of element greater than k in the subsequence ai to aj, right? So given a subarray, return how many elements are there which are greater than k, and k differs with each subarray as well, right? So that's what the problem is. We already solved this problem in the past using merge sort tree. In this particular video, I will link this video in the description down below. You can check it out if you are interested in that. So with merge sort tree, we have come up with a solution having complexity of order q log square n, where q is the number of queries and n is the size of the initial array, right? So in this video, as mentioned, we will be focusing on solving this problem using persistent segment tree, and then in the next video we'll look at when to use merge sort tree and when to use persistent segment tree. So with that, let's get started. So the problem is number of elements greater than k in the range l and r, right? So let's assume k is 1 and this is the given array, right? Now with persistent segment tree, we already have discussed in the previous video that we can solve this kind of problem if we can break the problem in two halves, wherein we will first solve in 0 to L or 0 to L minus 1 for that matter, and then we will solve for 0 to R, right? So if we are able to find out how many elements are there which are greater than k in the range 0 to R, and if we are able to find out how many elements are there which are greater than k in the range 0 to L minus 1, we can simply subtract these two numbers and get how many elements are there which are greater than k in the range L to R, right? So the problem boils down to finding out number of elements greater than k in the range, let's say 0 to I, right? So let's just replace this R with I. So let's assume this is our I. So we need to find out how many elements are there which are greater than k in the range 0 to I, right? So in this particular example, k is 1. So we can see number of there are 3 elements which are greater than 1 in this particular range. So the answer for this particular I would be 3, right? So that's what we need to find out. Now we already have solved this problem and problems of similar kinds in the past in several code forces problem. With one of these is enemy is weak, and there are a couple of follow-up problems as well which we have solved based on the same technique. So in this video, we will not be focusing on how to solve this problem. Rather, I will just give a brief overview. If you want to understand the entire thought process, you can refer to that video. I will link that video in the description and somewhere in the top right eye section. So the solution was, we will simply sort the array, right? And with this sorting, we got a mapping. So basically, we are saying that this 0 maps to this. The If this entire array was sorted, this 0 would be coming at position 0. This 1 would be coming at position 1. This 4 would be coming at, let's say, position X, and so on and so forth. So basically, with this mapping, we got where this element would belong if this entire array would be sorted, right? Now, what we will do with this? So basically, let's say you want to find out how many elements are there which are less than equals to which are greater than k in the range 0 to I. So what you will do, you will simply activate all the elements in the range 0 to I. So we have 1, so 1 maps to, let's say, this particular index, so we'll just simply activate it. By activating, we are saying everything else is 0, only the ones which are activated are marked as 1. So we activated 1, we activated 4, let's say, we activated 2, we activated another 1, and then we activated another 2, right? So these are all the active elements, all other are inactive. In other words, all other are the elements which are lying in the right? Now, to find out how many elements are there which are greater than equals, which are less greater than k, we can simply say, okay, I know all the elements which are greater than k lies in this particular range, right? So I will simply do range sum in this particular range, and I will get how many elements are there which are greater than k. Now, why range sum would work? Because we know only the elements which are in the left are activated, all other are marked as 0, right? So if we do a range sum, we will get how many elements are there which are activated, or in other words, which are in the range 0 to I. So we'll simply do range sum here, and we'll get the number of elements which are greater than k in the range 0 to I, right? So given a particular I, if we are able to build a segment tree on this particular array, we will be able to answer how many elements are there which are greater than k in any particular which are greater than k in the range 0 to I. Now k can be anything, depending on what k is, we will defer our queries. So basically, if k is 1, we will say, okay, find the range sum in this particular range. If k is, let's say, 3, if k is, let's say, 2, it means we have to find out the elements which are greater than 2. We will do the range sum in this particular range. If k is, let's say, 5, in that case, we will simply do range sum in this particular range. Basically, we'll simply return 0, right? So hope you get the idea. Basically, for a given I, we will simply build this particular array and figure out the range sum based on what k is, and that will give us the answer, right? So we have to find out this answer for all particular I, right? So we will need to build n number of segment trees. So for example, we'll start with the initial segment tree wherein there is no elements at all, right? Then we will simply say, okay, we'll build the segment tree for this particular range where I, or in other words, where I is this, right? And then we'll say, okay, I will build a segment tree for this particular range. In other words, I is this, right? So if we build a segment tree on this particular range, only one will be activated. So only one is activated, rest all are 0, right? So we build a segment tree on this, and then we will build the, for this particular thing, we will build a segment tree where only 1 and 4 are activated. So we see only 1 and 4 are activated, and we will segment tree on this. And in the same fashion, we will need a segment tree for this particular I as well. So we'll build a segment tree in which 1, 4 and 2 is set. So 1, 4 and 2 are set. So and so on and so forth. So we will build all these segment trees. Once we have all these segment trees, basically we are now able to we are now capable of answering all the queries of the form 0 to I. Whichever I is, we will go to that particular segment tree. Let's say I is 4, so in this case we will go to the fourth segment tree and say okay, or sorry, fourth segment tree, and say okay, give me, based on what k is, we'll figure out what is the range I need to start with. And once we figure out this range, let's call this range p. So once we figure out the starting point p, we will simply do a range sum in the range p2 and minus 1, and that will be my answer for a given I, right? So with one example it will make sense. So this is how the overall problem solution is. So let's look at how to build segment tree and do complexity analysis of this, and then we'll look at one example. So as discussed in the previous video, building persistent segment tree is based on the fact that we will reuse the previous segment tree and only change the nodes which are changing in the new segment tree, right? So if you remember, we need to build segment tree first on this particular array, right? So we, let's say this is the segment tree which is on this particular array. Now for the second tree, we know that only one index will change, right? So we'll simply go to that particular index. So we know one first position is changed, so we know that first position lies here. All the nodes up to the first position will be changed, right? So all these 4 nodes will be changed. The new value of this node will be 1. The new value of this node would be 1 plus 0, which is 1, right? And this node left child is this node's right child is this. Similarly, new value of this node would be the sum of left and right child. Left child would be this and right child would stay as it is, so it will be 1. And similarly, then this one again, left child is this and right child would stay as it is, so the value of this node is also 1. So in the same fashion, we'll build all the segment tree for building the segment tree for a single array. So the initial segment tree which we have built, so this particular segment tree, to build this segment tree, we know we require order and time, because this is a useful segment tree, right? Now order and time and order and space as well. So this is space and this is time. Now for building a new segment tree, or for building the segment tree for the second array, we will be changing order and nodes, right? So we will be changing these all nodes, which is order login. So with each array, we are introducing login new nodes, and we will be building total n number of segment tree. So in total, we'll be introducing n log n nodes. So this is the overall space complexity, and the time complexity will also be exactly same, because we will be iterating over only all those log n nodes which we are modifying. All other things will stay as it is. So the space and time complexity to build the segment trees for all the for all the array is order and log n, right? Now let's look at how to do queries. So let's say you need to query in the range 1 to 3 with k equals to 2. In other words, we have to figure out how many elements are there which are greater than 2 in the range 1 to 3. So this is the range, and we need to figure out how many elements are there which are greater than 2, right? So how we will do this? We'll first figure out, as we discussed, we'll first figure out the number of elements greater than 2 in the range 0 to 3, and then we'll figure out number of elements greater than 2 in the range 0 to 0, and we will subtract these 2 elements to get the final result, right? So for the first one, number of elements greater than 2 in the range 0 to 3, we will simply go to the third segment tree. We'll simply go to the third segment tree, and what we will ask, we know that third segment tree would be storing a version of this array, right? And we need to find out number of elements which are greater than 2. So we'll simply do range sum in this particular range. So we'll go to the third segment tree, ask for the range sum in the range 0, 1, 2, 3, 4, 5, in the range 5 to 7, right? And then in the same fashion, we will go to the 0th segment tree and ask for range sum again in the range 5 to 7. So let's look at that. So this is the 0th segment tree, because basically everything is 0, and we need to find out the sum in the range 5 to 7. So if you look at the sum at range 5 to 7, you will include this node and this node. If you go via the segment tree query method, you will include this node and this node. So the addition of these two nodes will yield you 0. So basically number of elements which are greater than 2 in the range 0 to 0 is 0, right? Now how many elements are there which are greater than 2 in the range 0 to 3? So basically we will go to the third segment tree. So this is how the third segment tree would look like. Basically we have 3 elements. Again we look at the range 5 to 7. So if you look at 5 to 7, these and this node you will be summing up. So in total you will be getting 1. So number of elements which are greater than 2 in the range 0 to 3 would be 1. So you will just subtract these two and you will get number of elements which are greater than 2 in the range 1 to 3, right? So hope this entire thing makes sense. Only what is the, like, how much, what is the time complexity of doing each query? Notice what we are doing. We get a query LRK. For what we decided first, we first decided what is the value of k. Based on that we figured out what range we need to query, right? So we will just do a simple upper bound or lower bound. So this will take order log n time. So order log n time to just figure out which range to query. And then we will query two segment tree. Querying one segment tree would take log n time, and querying two segment tree would take 2 log n time. So in other words, it will take 2 log n time to query two segment tree, and then we'll subtract the results. That will be order one operation. So in total, this is the overall time complexity for a single query, and we have q number of queries. So this is the overall time complexity. So the complexity is n log n plus q log n. Remember the same problem we have solved in q log square n using merge sort tree, but now we are able to solve this in q log n using persistent segment tree. So this is just one difference between merge sort and persistent segment tree. But as promised, I will upload a different video making it very clear when to use what. So next we will be looking at code. That is the main thing in this video. So the code is straightforward. We will need to build persistent segment tree. That's the first piece. So how to build persistent segment tree? We discussed already. We will first prepare a empty tree. In other words, we'll first prepare this kind of tree where everything is 0, but every leaf node or every node is representing one point or one index in this particular array, right? So this is what we need to build. Now how to build this? Very simple. We have built this structure many times in this series. We'll use recursion. Basically we'll start from the root node is 0 to 7. We'll say, okay, build me the segment tree in the range 0 to 3. We'll say build me the segment tree in the range 4 to 7, and then I will simply create a new node, point the left pointer of this new node to this left tree, point the right pointer of this node to the right tree, right? And one more thing to note here is, as mentioned in the previous video, here we will not be able to use single array, or we can use, but it is bit harder to use the single array to represent this structure. So we'll be using pointers to represent this tree structure completely, so that it is easier when we create new nodes and start pointing to the left and right child, right? So we'll be creating a structure which have 3 different elements. The structure looks like this. It has value, left pointer and right pointer, right? So we will first build this initial tree, and as discussed, we'll use recursion. We'll say, okay, I need to build the tree for L to R. I will simply build the tree for L to M. I will build the tree for M plus 1 to R. I will create a new node and point the left child of that new node to this left tree, point the right child of this new node to the right tree, right? And the base case would be where L is R. Or in other words, when we reach the leaf node, so in that case, the left and right child pointer would be null, and the value of this node would simply be 0. So that's what we have done as well, right? Now, once we have the structure built, this is what we will do in the constructor. Now, once we have the structure built, we have to do two things. First, we need to build more segment trees, right? Which will be by updating some of the nodes, right? And second, we need to do queries. So let's look at the update part first. So we need to, let's say, update a particular index I with a given value v, right? So this is what we need to update. So in this case, what we will do, we'll simply go all the way to I. Let's say I come somewhere here, so we'll go all the way up to I. We will simply we'll simply replace all the nodes from root to that particular node, and we'll start from the bottom, update this value to v, because we know that the value of this node would be v. So we'll update the value to v. Now for the parent node, we'll point the left child to this new and the right child to the already existing right child, right? So what we need at this stage, we need what was the original parent, so that we can actually find its right child and actually point the new parent's right child as well, right? So this is exactly what we have done. For building a new version, we take the previous root, the index to update, and the value for the new index. And this LR basically is representing which range we are currently working with, right? So we will create new node for every node that we will visit, right? So as discussed, we will visit all the way to I, and every node that we have visited, we will create a new node for that. So for every node we are visiting, we are creating a new node, which will be the new representation in the new tree. Now if the index lies in the left side, then if index lies in the left side, then the left pointer will be updated to the new node which we'll be creating, and the right pointer would stay as it is, right? Which is the right pointer of this particular node, right? So that's what exactly we have done. If index lies in the left, we will update the left pointer with the new root that we will be getting, or that we will be building, and right pointer would stay as it is. Whatever the right pointer of the previous root was, that same right pointer would stay for the new node as well. Now in the same fashion, if it is in the right side, we will just simply do opposite. Left pointer would stay as it is, and the right pointer would be updated to the new right pointer. Now once these two pointers are pointed correctly, we will simply update the value of the current node with the summation of left and right child, because we need to actually find out the range sum in a particular range. So we'll simply maintain the summation in a particular node of segment tree. Now the base case is simple. When we reach the leaf node, we actually reach the node which we want to update. So we'll simply create a new node and update its value to v, and left and right child would be null and null. So that's what the base case is. So just to reiterate, for building a new version, we will look at the previous root. We will see if for every node that we are visiting, we will create a new node. For the new node, we will see if we are updating, or if we will be updating the left node or the right node. Based on which node we will be updating, we will either update the left pointer or the right pointer, and the other pointer would stay as it is and will be pointing to the node which the previous node was pointing to, right? And once we will go from bottom to the top, and leaf node we already know the value for, which is v, which is a new value. And once we are visiting the node above leaf, we will simply be summing up the value of the left and the right child to get the actual value here. Now this is how we will be building one new segment tree on top of an existing segment tree. So we will be calling this function n number of times in our problem. So we'll look at that, but this is how we will be building a new version. Now final thing is the query part. So the query part is straightforward. So if you remember, this entire building part is something which is bit tricky, but once this segment tree is built, it will look something like this. Either the pointers will form a segment tree like this or this or this or this, right? So basically what we need to query on is a regular segment tree. So the query function would work exactly like a regular segment tree. Only difference is, in previous versions we have seen we have stored the segment tree in an array. So we maintained, if you remember, L, R and I, where L and R is the range which the current node denotes, and I is the index in which the value is stored for the current node, right? But now, as we discussed, this is not an array. Instead, we have a node, complete node for a tree with a left and the right pointer. So that's the only difference. So let's look at the code. The code is exactly similar. We have L and R. Instead of I, we just have a root this time. And this X and Y is the range which we need to query for. Now, the base case is if the current node range lies completely outside of X and Y, we'll simply return 0. This is the neutralizer value because we are doing a sum. If current node completely lies within the query range, we'll simply return the value of the current node. Otherwise, we will go both left and right and sum the value up, right? So the query is exactly same. Now let's look at the driver code, which is this is where we are taking the inputs, right? And if you remember, after taking the input, we have to first sort the array and build something like this, and we have to build the mapping as well, so that when we see 1, we know which index to update, right, or which index to activate. So we have to first sort the array such that we also have the mapping, that which 0 index points to which index in the sorted array, right? So that's what we have done. We will simply sort the array, and we maintain a map as well for the indexes, right? So these all things we have already discussed in this video, so you can watch that if that is something unclear here. So I'm just glossing over some of the details here, but we build the index array. Now once the index array is built, we need to build the segment tree for the range 0 to I, right? So for every I, we will simply look at which index I need to activate, and based on that I will activate that, and will change the value of that particular node in the previous segment tree, right? So whatever the previous segment tree was, I will just change the value of that particular node. So that's what we have done. For every index, we figure out which index to activate and simply update the value of that node to 1. So what this will do, this will simply call this build new version and take the last segment tree that we have built and update this particular index with this particular value, right? So this entire thing will give us a new segment tree or a root of a new segment tree, and we will simply push back the new root to this roots array. This roots is just a vector of node, right? Now this roots array will contain the root of all the segment tree from 0 to n, right? So this roots array will contain roots of 0 will contain this particular root of this particular segment tree, roots of 1 will contain the root of this particular segment tree, root of 2 will contain this, root of 3 will contain this, and so on and so forth, right? Now once we have built all the segment trees, now it's the time to query. For every LRK, what we have to do, we have to first figure out which range to query. We have to look at k and we have to figure out which range to query in the sorted array. So if you remember, for a given k, we need to first figure out which range to query. So for that, we have to simply do an upper bound on this particular sorted array, So that we have done, we simply do an upper bound on this sorted array ARR for the value k. And once we figure out the index, we'll simply look if index is post the array, or if the value k is actually greater than the largest, sorry, if the value k is actually greater than the largest value here. So if the value of k is, let's say, 5, so in that case you don't have any index, any element at all. So in that case the answer would be 0. Otherwise the answer would be, will query the segment tree or the rightmost, will query the segment tree for 0 comma r, and we will query the segment tree for 0 comma l minus 1, right? And subtract the value to get the answer. So that's what we have done. We written a query method that will look query the segment tree for the rth, or that will query the rth segment tree, and will query the l minus 1 segment tree for this particular range after index to n minus 1, and we'll subtract the value of both and we'll return the answer. Now this query method is just just taking care of which route or which segmentary route to query for, and we'll call the internal query method, right? So hope this entire code makes sense. I would strongly encourage you to try and code this entire thing by yourself and get it submitted in SPOS as well, because that's where you will be able to understand if you have missed some edge cases in your implementation, and you will get much better understanding of this particular concept. So with that, we'll end this video now. If you have any doubts in any of the concept discussed in this particular video, feel free to post them in the comment below. I would be able to answer. If you like the video, give it a thumbs up, and if you want me to discuss any particular problem about persistent segment tree in the future, feel free to post them in the comments as well. I will try to cover them as well. And if you understand this problem, there are a lot of other problems as well, which there are some problems which we have already discussed in the past in this channel, so you can give them a try at least and see if you are able to convert the solution using into persistent segment tree solution or not. And with that, in the next video, as promised, we will look at the differences where merge sort tree can be used and where persistent segment tree can be used, or vice versa, because you can see there are a lot of questions are common here. So well-run queries are here, well-run queries is also here. Kth num is here, mkth num is also here, and similarly we also have KQuery, which we discussed in this particular video. So there it might seem that they are exactly similar, but there are differences and there are major differences. So we'll look at that, and I will see you in the next one. Thank you.